hot and cold spots. In Fermi contour, I have no three hands, so we will use this one. Thank you very much. Because we are staying on the position of fundamentalism, and we wish with one and the same Hamiltonian to describe superconducting properties of the overdoped and optimally doped superconductors, and simultaneously the normal state properties. Hot and cold spots, they was invented 20 years ago as a phenomenology, but now we are happy to derive this phenomenology from the microscopic Hamiltonian. So those are ARPES data for so-called hot spots along the Fermi contour. And we are trying to explain how those hot spots emerged from the standard model of pairing mechanism. What is the standard model of cuprate plane? We have 4 different orbitals, oxygen orbitals, very important 3D orbital, and from time to time people introduce Cooper 4s orbital, which is extremely important from our point of view. We are using linear combination of atomic orbitals, and T means transfer between different orbitals. Linear combination of atomic orbital is the basis of the chemical intuition, and we will apply this chemical intuition into the physics of superconductivity. Sorry for this incompatibility of the equation of the computers, but I will skip that. Wave function is linear combination of wave functions of different orbitals, and we have single particle orbital, which is starting point of statistical considerations. So in the picture we can see not only Hoping integrals, which are very famous, but also Kondo exchange two-electron interaction. This two-electron interaction is actually correlation. One s electron becomes d electron, and simultaneously one d electron becomes s electron. This is so-called SD, or Kondo interaction, and the name of Kondo I have listened in this conference at least 4 times. So we included in Hamiltonian Kondo interaction as an exchange pairing mechanism. Let me see some formula where something can be seen. So from this exchange interaction, this is a cartoon for exchange interaction, Kondo exchange interaction. Imagine what is S electron. S electron is like a kamikaze electron which is falling to the nucleus and resurrecting then, and D electron is rotating in a circular orbit. But 2 electrons can change his orbitals, and this is SD exchange mechanism. There is already a book systematizing those technical details. I will skip all those technical details which are standard, but we are presenting those orbital, those calculations. Formulas cannot be read in this representation. So, if we have standard BCS reduction made actually by Bogolyubov, we derive some BCS pairing kernel, which is factorized by a function with from different wave vectors. And running ahead to my presentation, I will say that the same kernel arises again from the Fermi-liquid reduction of the same Hamiltonian. I will skip unreadable details. Actually, I have a PDF of our calculation. We have an abridged version. Everybody asking I can give you my unabridged version of the PDF. So this is the standard band structure, which is repeated by a lot of local density approximation, and this is atomic wave interpolation of the well-known electron band structure. We have a conduction D band and Fermi level crossing this D band. So in our kernel, we obtained analytical solution for the factorization, and gap anisotropy is proportional to two well-calculated functions. This is hybridization function, which has a saddle point shape, and this saddle point is crucial for the understanding of cuprate gap anisotropy and hot and cold spots. This is velocity calculated from the band structure, which is standard. In BCS theory, we have tangens hyperbolicus integrand, which can be drawn for this rounded square shape of the Fermi surface. And what we can see is those are data by Campuzano. We have on Fermi surface. We have D-type gap anisotropy, and those experimental data are ARPES data for the by Campuzano for the energy gap of optimally docked cuprate. We have integrand for BCS theory, but BCS theory and pairing is just starting point of our consideration, because I consider that pairing is slightly trivial. Much more rich for effect is the normal phase. What is the most remarkable observation in electron band calculations? This is Pavarini-Anderson correlation between the shape of Fermi contour and critical temperature. We know that practically all phase transitions are created by some interaction. But how is possible shape of the Fermi surface, which is a property of non-interacting electrons, to correlate so perfectly with the critical temperature? Because Pavarini and Anderson takes some points in the diagonal and these points, and from those points they calculate some dimensionless parameter which perfectly describe a correlation between the shape of Fermi contour and critical temperature. No explanation. This paper has about 200 citations, but no one of those citation is related to some microscopic explanation. Moreover, it is achievement by Albert. He put the red crosses. Red crosses are experiment. ARPES experiment together with electron band calculations, two absolutely different methods, gives one and the same methods. And the continuous line is our initial theory. Theory is not so good, but there is no better theory at the moment. This is a BCS treatment of the Kondo exchange interaction, which describes this correlation. Now I am trying to present the Landau-Fermi liquid reduction of and self-consistent approximation. And again, if we apply the Landau theory of Fermi liquids, we again from the same Kondo Hamiltonian obtain the same factorizable kernel, which is very important for the Fermi theory. And no, I put in archive, but it is blocked already 2 weeks. Archive now is not working. 3 weeks ago we put in archive, but still is not accessible. So I cannot make better solution, but I have to make a pantomima. So we have conductor which has layers. We have parallel layers. Between those layers, we have vacuum. We have electric field which can fluctuate between those layers. Who could be flying to the blue sky? We have electric field between layers, and this is like a plane capacitor. In every plane capacitor, we have charging energy, which is determined by the thermal fluctuations. And we are obliged to take into account the thermal fluctuations. Thermal fluctuations cannot be forgotten. They have to be taken into account. But fluctuations of electric field is related to fluctuations of density. Fluctuations of density is something very important. Fluctuations of density is related to as a scattering mechanism. We are taking microscopic Hamiltonian, which pairing, and put this Hamiltonian in old theory of Lord Rayleigh for scattering of waves by density fluctuations. And we succeed to describe the this phenomenology of hot and spot regions. Those are our calculations. I mean, colors describe intensity of scattering, single particle scattering along the Fermi contour. So at those places where experimentalists by ARPES observe hot spots, we calculate strong scattering of charged particles. So this is our function which analytically describes scattering rate. This is Kondo scattering rate, two-channel scattering rate by Kondo interaction, and we have hot spots, and also we can calculate phenomenology of Drude conductivity. Drude conductivity is parameterized by some effective scattering time, but this scattering time has to be integrated, and in spite of the poor quality of the written, we can explain our final result by pictures. This is theoretical picture for Fermi contour and our hot spots. Those are ARPES data. Albert put our calculations on the ARPES data, and this is theory over experiment. So what is the final message of our presentation? One and the same microscopic Hamiltonian as the microscopic Hamiltonian can describe phenomenology of anisotropy, strong anisotropy of scattering of normal charge carriers, and simultaneously pairing anisotropy of cuprates. This is, I think, a good beginning, and theory is not very precise, but this is like a submarine which can fly or airplane which can dive. We can go in different area. I think that's it, and we'll stop.
Now, let me start then the discussion. So it's very interesting if, I mean, from a microscopic model, you can predict there is hot spots and cold spots. You know that in a less microscopic model, like theories of spin fermions, you could have hot and cold spin, for example, from antiferromagnetic fluctuations or from charge ordering. How do you make the link with antiferromagnetism or charge ordering? Can you get them from your microscopic model? Do you think your Kondo interaction? Formula came back.
Yes, it is. I think this approach is very flexible and can be applied in many different.
We missed to work with good formulas. I mean, it's like.
But with imagination and strength of the
mind, yeah.
The mind, you compensated this. So this, what is necessary? It's necessary to calculate electron band structures from LKO model. This is already matrix 4x4 or 6x6.
But can you predict that it will give antiferromagnetism or charge ordering from this Kondo interaction? Can you predict that it will give one of the two to be coherent with kind of phenomenological description we have?
I think yes. It is matter of time of manpower. I think it is possible the same approach to be applied in a lot of systems in which exchange interaction dominates.
So then it will be very interesting to see if it produces charge ordering, what is a wave vector it gets.
Yes.
Because those wave vectors are very notoriously difficult to get from any microscopic model, and the one observed by X-rays and Fermi surface reconstruction. So it would be very nice to see whether you can get them.
I'm here.
Okay.
Searching for people thinking in this direction, and I forgot to congratulate organizers for such good running conference after this delay. This is a big success. Again, our biofield to be fixed on the superconductivity and magnetism.
Okay, this is true. I agree. So let's congratulate Ali who is in the room.
Yeah.